Hey everybody, it's Brandon from STEM Tutor Club, and today we're going to go over a 6-step process that will allow you to solve any related rates problem. Related rates problems are some of the most difficult problems that you'll have to solve in a typical AP Calculus AB or BC course, which is why it's important to have a process that you can follow every time. But before we get into that process, let's talk about what we actually mean by related rates. In a problem like this is a standard related rates problem that you'll learn. We have a ladder sliding down the wall. And the key idea is in the problem, they'll give us information about how fast the top of the ladder is sliding down the wall. And we can actually use that information to figure out how fast the bottom of the ladder is moving away from the wall horizontally. Now, the way we actually do that is by basically combining geometry with calculus. So the key idea is that at any point in time, no matter how far the ladder has slid down the wall, it always makes a right triangle right here, like underneath the ladder. We always have, in this case, it's a right triangle. And if we have a right triangle, that means that Pythagorean's theorem is always true. A squared plus b squared equals c squared. So even though it's like as the ladder slides down the wall, we constantly make a different right triangle. The fact that it's a right triangle at every point in time means that Pythagorean's theorem is true at every point in time. So we can take that equation, and essentially what we can do is take the derivative of both sides with respect to time. And after we do that, we no longer get an equation that's just relating, y. So this would be like y as a function of time. This would be x as a function of time, hypothetically. We would, if we take the derivative of the Pythagorean theorem in this case, we would no longer just get a function that relates y to x, but we would get a function that relates dy dt to dx dt. In other words, there's an equation that tells us that the rate at which the ladder is being kicked out away from the wall here is related in some way to the rate at which the ladder slides down the wall here. Hence the term related rates. In other words, the related rates of change of different measurements in your diagram over time. So that's conceptually what we're dealing with related rates. Now let's dive into the actual process. So here it is. Here's the process. Now the way I do it, it's a 6-step process. There are other people who do it differently. They have different, like a different number of steps or different steps, but this is the one that I like the most. Now we'll go into each of these in detail. We're going to actually apply them to a typical related rates problem here so that you can see how we actually apply these. In this video, we're going to use this problem. So a tank of water in the shape of a cone is being filled with water at a rate of 12 cubic meters per second. The base radius of the tank is 26 meters and the height is 8 meters. And then they're asking, at what rate is the depth of the water in the tank changing when the radius of the top of the water is 10 meters? This is a problem that I pulled from an online website that I really like, Paul's Online Math Notes. So here you can see this site, and this is really good for working through problems. On their website, if you just Google Paul's Online Math Notes related rates, you can basically get a lot of practice problems where they walk through each step line by line. So this is a really good resource if you're looking for extra practice. So here we're going to actually use the process that we talked about above and apply it here. So the first step with any related rates problem, because again, related rates problems really combine geometry with calculus. So the first step with all of these is to draw our diagram. So here, just reading through here. So we're talking about basically a tank in the shape of a cone being filled with water. So the first thing that makes sense to draw, I think, is the tank itself, which is a cone. Let me draw that. And again, this won't be perfect. Luckily, this is an art class. But basically the idea, so we have that. So this is the cone. And then the key idea is it's being filled up with water. Actually, let me make a little bit more room here. I'll scroll down a bit. But if we want to imagine it being filled with water, you can kind of imagine, you don't have to really draw this part. This isn't as important, but you can imagine basically a pipe with water just filling it up. So water is like falling into the conical cylinder, the cone, or sorry, not conical cylinder, the conical tank of water. So, and then it's basically, you can think about it, we're filling up the water level of this tank over time, if you want to think about it like that. So the water is basically just falling in right here and filling up this tank of water. So this is kind of the situation that we're dealing with here. So this is kind of the basic diagram. And just looking through, you can see if there's anything else that we need. So the base radius of the tank, they're giving us a lot of information here, but this is fundamentally what the diagram is about. So there we go. That's step one. And you should do this on every related rates problem. You always want to visualize it because, again, we're using geometry here. So like you basically need to visualize it to make sense of what's actually happening. The second thing that I like to do is to label each one-dimensional measurement as a function of time. Now, why do I say only one-dimensional measurements? So basically, we could like at any point in time in this problem, for example, we could call this entire volume right here the volume of the cone of water, and we could like label that. So we could just like highlight that in a different color and call that like V of T if we wanted to. That's the volume of water in the tank. I do not like doing that because you can see that I have to basically scribble over everything, or I have to highlight everything in order to do that. In my opinion, that just makes things too complicated. The way I like to do it is just to focus on one-dimensional measurements. So like height, width, length, in this case, radius, those sorts of things. The other thing, so like specifically, the things that are relevant here, in my opinion, is this, the radius, and then I'll also do this, which is the height of the water level. Now, one other thing I should mention is that I like to label, this is something that I do. I don't see this a lot in other textbooks, although in my opinion, they should be, like other textbooks should do this because I think it's a good idea. But what I do is I basically label these as functions of time. So I'm just crystal clear from the beginning that we're dealing with functions of time. So I'll call this like H of T. So this is like the height of the water level. And then I'll call this R of T. That's the radius of the water level, like if we're looking at it as an upside down cone at each point in time. And this is something that's important to point out. With related rates problems, a lot of times, like other textbooks, they'll just call it R and H. The reason I don't like doing that is because it makes it seem like we're dealing with numbers. We are not dealing with numbers. These measurements are not numbers. They are functions of time. They change over time. So given at a specific point in time, they are a certain number, but that is always changing. So like in this case, as we pour in more water, this radius and this height are always going to change. So in general, they are functions of time. And this is really helpful when we get down to step 5, which we'll talk about later, when we take the derivative of both sides. Basically, if you have just numbers here and you try to take the derivative, what's the derivative of a constant? Well, that'll be 0. That is wrong. We are actually taking the derivative of functions of time. And I just like to label that here just so I remember it later. So that's sort of something that I do, but I do recommend that. So there we go. We've labeled the important measurements. Now, number 3, we're going to extract all the information from the word problem. And when I say extract, I mean something very specific, and you'll see what I mean. And by the way, I recommend doing what we're about to do on this problem for every single word problem that you do in math for the rest of your life, basically. The reason is because it just makes every word problem easier to think about. The reason that word problems are so hard is that basically there's a lot of information being thrown at you, and it's very difficult oftentimes to think about what information is important, what's not important, what have I used, what have I not used, and it's very easy to get overwhelmed, whereas you typically don't have to deal with that in simpler problems. But with word problems, that's a big concern. So what I like to do, I like to literally go word by word, line by line through this paragraph, like through the actual problem, and just cross things out and turn them into equations. So let me show how we do that. And by the way, in this case, for related rates problems, there's only four possibilities for the information in the word problem. Number 1 is we should basically label something on the diagram. That's one possibility. The second possibility is that we should label that we should basically turn it into an equation. So like if they write in words here, the height of the tank is 8 meters, we would say H equals 8, for example. And you'll see exactly how we do that. That's the second possibility. The third possibility is that they're telling us what they want us to find, basically, for the problem. So like specifically when you see a question mark, that's a sign that's where they're telling you what they want you to find. That's where they actually ask you the question. Whereas with the rest of the problem, they're basically just giving you information to answer that question. So those are 3 options. And then the 4th option, which happens more than you might think, is that the information is useless. We should just cross it out and ignore it. Now the problem is when you're doing a normal related rates problem, it's still you're still looking at that information even though you should ignore it. So it's actually very important to cross out things that are not going to help you. So those are the four possibilities, and we're just going to go line by line, phrase by phrase, word by word, and just basically do that process. And after you're done with step 3, you should basically have the entire problem crossed out. Now, if you're taking a test, maybe you don't want to cross it out. Maybe you want to be able to read it still. So maybe you underline it instead of cross it out. I'm just going to cross it out here. So here, a tank of water in the shape of a cone. We already drew that, basically. So yeah, we already drew a tank of water in the shape of a cone. So we don't need to focus on this anymore. Is being filled with water at a rate of 12 cubic meters per second. So here, if you think about this, basically the way I interpret this, I just say dV dt equals 12. Because and then the units are also helpful here. So if you see these units, cubic meters per second, cubic meters, that's a measure of volume. If it was square meters, that would be like area. If it was just meters, that would be like some one-dimensional measurement. So these units are also helpful. But basically the idea is and this is where there's kind of a small leap in logic, but if we're filling water into the tank at a certain rate, that's going to increase the volume of the water, the volume of this cone, in other words, at a certain rate. So that's basically the idea. This sentence is effectively telling us that dV dt equals 12. And then I'll cross that out. One other thing I'll mention, by the way, this happens sometimes. Sometimes there's like small tweaks to this problem where water is actually dripping out of the bottom. So they'll say like water is dripping out of the bottom at 12 cubic meters per second. In that case, you would just say that dV dt equals negative 12, because whenever water drips out of the bottom, the volume decreases. So hopefully that makes sense. The next part, the base radius of the tank is 26 meters. Okay, so what I would say here, so they're talking about the radius of the tank. And by the way, that does not change. So this thing should not be a function of time. So I'll just call that 26, what they told us. So the tank itself is a solid. It does not change. What changes is the water level. As the water level rises, that basically becomes a bigger and bigger cone as it's being filled up. But the tank itself does not change. So you can write this, and you should write this as a number, not a function of time. We only want to label functions of time if the measurement changes over time. But if it stays the same, then you can just label it as a number. Here, the base radius of the tank is 26 meters. You can get rid of all those words and just write 26 here in the diagram. And don't you see how this is like a better idea, like in terms of like minimizing what we have to worry about? Because like all these words, like most of these words are useless. Like all we really need is that like radius of tank is 26, but there's a lot of extra words here that we don't need to focus on. So if we keep making trades like this, so like I basically take this, turn it into dV dt equals 12. I take this next part and turn it into just a line on the diagram with 26. Just cross this out. That's the shape of the cone. If we keep doing things like that, we're gonna basically reduce the amount of information that we have to worry about, which is the whole point. That's good. Then they're saying the height of the tank is 8 meters. So the way I would do that, I'll label the diagram. This thing equals 8. And again, the way I drew it, it makes it not look like that. Obviously, 8 should be way smaller than 26. So this is actually a much wider cone in reality. It doesn't really matter. Like geometrically, like we'll get the right answer even if we didn't draw it perfectly to scale. That's good. And then they're saying, at what rate is the depth of the water in the tank changing? So at what rate is the depth of the water in the tank changing? This is where you can think about what function did we use to represent the depth of the water? So the depth of the water is really like the height of this cone. So the way I interpret this, at what rate is the depth of the water in the tank changing? I just say dH dt. That's the rate at which the depth of the water in the tank is changing, or that's how I look at it. And specifically, they're not telling us what that is. This is actually the part in the problem where they're asking us the question. Every problem should have one of those, unless it's multiple parts, and then for each part, there'll be a different question. But here, in general, the way I like to represent this, I like to say dH dt equals question mark, because that's effectively what they're asking us to find. So at what rate is the depth of the water in the tank changing? And then usually the way these problems go, you usually see the word when, and then sometimes it's not exactly the word when. Sometimes they'll say like if or suppose that blah blah blah. But basically they always mean when. So what is this measurement? The rate of change of a certain measurement in the diagram. In this case, they're asking for the height. They could have also asked for the radius, but in this case, they're asking for the depth or the height. And then when, and then usually there's extra information. So when the radius of the top of the water is 10 meters. So now this is important. They're not talking about the radius of the top of the container or the tank of water. They're talking about the radius of the top of the water itself, which does change over time. So that is what we labeled R of t. So basically when R of t equals 10, they're telling us. So that's how I would do that. So there we go. So that's number 3. So what have we done essentially? We've taken a bunch of words and we've turned it into a diagram, which is going to be helpful for us with the geometry and basically a set of equations. Now, I would argue I would much rather do a problem like this visually than do a problem like this in words. So essentially what we've done is we've converted the problem from words to this, and now this is going to be much easier for us to understand. That's good. Now let me scroll down a little bit just so we have room. So now we're dealing with a situation like this, and actually let me move this over just so we have some more room. So far, actually, now we at this point you can basically just forget the words and just everything should be crossed out. Now this is the problem. This is all we have to think about. I don't know, like I said, I don't know about you, but I would much rather, like, this is much clearer to me than the words. So, okay, yeah, we know dVdt, we're trying to find dHdt. When R of t equals this, it's a lot less to think about than all the words in the paragraph. So if you do step 3 right in this process, you should have a much more simplified visual representation and much clearer equations to actually use. So that's good. Now with number 4, we want to come up with a geometric equation that relates what we know. Here's all the stuff we know, and also on the diagram, relates what we know to what we want to know. And then we'll have to watch out for this. Sometimes you need more than one. So but for in every problem, you need at least one. So how would we do that? So what do we want to know? We want to know dHdt. That's what we're trying to find in this problem. dHdt equals question mark. Now here, what I'll just say is that if you look ahead slightly to step 5, you see how we'll take the derivative of both sides with respect to time. So I guess what I would say, or the way that I think about it is, because again, with geometry, we're trying to find a geometry equation. Geometry is not calculus, so there's no derivatives in geometry. They're just like basically like this measurement is related to that measurement by a geometric equation. So the key idea is that in step 5, because we're going to take the derivative of both sides, what we really want is we want an equation with h in it in step 4. So if we can find an equation with h in it, then if we take the derivative of that, then dHdt, the derivative of h with respect to t, will pop out. So that's kind of what you can think of that. So as you look at these like basically as you look at all the information you know and what you want to know, think about basically if you have a derivative, just find the regular version of it, not the derivative. So like if we know dVdt, the rate of change of volume with respect to time, we want to find the volume. dHdt, we're trying to find the height or the depth. And then R, we want to find the radius. So basically we want a geometric equation that relates the volume of this blue cylinder, or not cylinder, cone of water to its radius and its height. What would that be? This is where some creativity comes in, by the way, but hopefully it makes sense. This would be the volume of a cone. Volume of a cone is what we want to use here. And this is where you do have to be you have to at least be aware of some of the key geometry equations, but here I'll just do V of t. And by the way, the same thing that I mentioned on step 2 as a function of time, I'm doing that here. I'm not just saying V equals pi or whatever it is in terms of R and H. I'm being crystal clear that we're talking about like V as a function of time because it changes over time. The volume, the radius, and the height are constantly changing. So that's going to be, if you remember the equation, it's going to be pi over 3, and then I'll say R of t squared times h of t. So this is like the volume equation for a cone, but instead of just V equals pi over 3 R squared h, I'm making everything a function of time. Again, that's something that I do, but I do recommend it. So that's what we're trying to do here. So that's step 4. So come up with a geometric equation that relates what we know to what we want to know. So we've basically done that. Now, step 5 is take the derivative of both sides with respect to time. Now, we could just do that, but I guess what I'll say is we're going to run into a bit of a problem. And hopefully you'll see what I mean here. Let's not actually do that yet, but let's plan it out. So hopefully it makes sense that if I do dv, or if I take the derivative with respect to time on the left, I'll just get dv dt, which we already know. So that's good. But if I take the derivative on the right-hand side, hopefully it makes sense here. It's going to be a little bit more complicated, but basically it's going to be the product rule because we have r and h, two different functions of time. So in general, on the right side, I will get r, dr dt, h, and dh dt. We'll get all 4 of those. But I only know 2 of those. So dh dt, that's what I'm trying to find. And r of t, that's what I know. I do not know h of t, and I do not know dr dt, which will show up in this equation. So if we take the derivative as it is right now, we will end up with a bunch of things that we don't know and that we won't know what they equal. Meaning we'll have one equation with multiple unknowns and we won't be able to solve it. This is where this sometimes comes into play. Sometimes you need more than one geometry equation to get rid of some of the variables in your equation so that you can actually solve it. So here, if you think about it, basically what we want in our equation, we're trying to find dh dt. So if we're going to take the derivative of this in step 5, so in other words, I guess what I'm saying, let me back up a bit. We're not done with step 4, I guess, is the punchline here. So we found one equation, so that's good, but we apparently need another one because right now, if we try to go to step 5, we're going to end up with a bunch of stuff that we don't know after taking the derivative of both sides, and then we won't be able to solve it. So here, this is where some planning comes in. So we have to look at this and say, what is our end goal here? Remember, our end goal is to figure out what dh dt is. So after we take the derivative of this thing, dh dt must pop out somewhere in order for us to solve the equation for dh dt. That has to happen. So that means h of t right now has to stay in our equation. So h of t, this has to stay. So this has to stay. Or this has to stay. Now, if this has to stay, that means the other equation. So this can stay. By the way, this can stay because we already know dv dt. So as long as we know what the variable is going to be when we take the derivative, that can stay. Which by process of elimination means that this has to go. Or this has to go. We need to substitute things in so that we can get rid of that. Now, how do we actually do that? Basically, like I said, substitution, we need to find what r of t equals in terms of one of the other variables, either v or h. So in other words, if we can find r as a function of h of t or v of t, two functions that we do know, then we'll just be able to plug in wherever we see r of t, we'll be able to replace it with that function of v or h, which is the whole idea, which is the whole goal. So the question is, and again, we need another geometry. We can't just make up an equation. We need an equation that's true based on the geometry. And this is where things get tricky. And by the way, I'll add a side note here. With related rates, there's about, depending on how you count, there's 8 kind of typical related rate geometries, and then there's maybe 4 to 5 extra super difficult ones. So if you're curious about, oh, how would I ever think about these other things? If these like leaps of logic to come up with the geometries seem difficult, they are, first off. The best way to solve that is to actually just practice the like 8 to 15, or actually 8 to 12, I'd say, different types of problems. Because after you've seen all of those, you're very likely to see, like any problem you see in the future is going to be very similar to that. So you won't have to come up with this from scratch every time, I guess is what I'm saying. After you're familiar with like how the geometry on some of these problems go, you'll be able to figure out the other ones much more easily. But here, either way, if you've seen a problem like this or not, what we really need to do, the trick here is to look at the cone from the side. So look at cone from the side. So if I do that, hopefully it makes sense that the cone is actually going to look like a triangle in that case. So let me draw this. The cone is actually going to look like a triangle where this is 26. And again, I know it's not drawn the scale, but that's not That's not super important, but it's going to be 26 by 8. And then the water level is going to create another triangle inside here. So another triangle inside. And then that, remember, is going to be something that those measurements are going to change over time. So that's why we have R of T and H of T. Now, again, how would you think to do this? Basically, like if you're clever, maybe you could figure out the first time after looking at it for long enough and trying a couple things. But honestly, like the best way is to have seen a problem like this before. So if you like all these like related rates cone problems, they all follow the same general strategy. So this always turns out to be a step in those problems. There are other problems where you don't need to come up with a second equation, but here we do for this one specifically. Now here, so this is like the diagram looking at it from the side, but what actual equation would we use? Similar triangles. So similar triangles. Why? And again, this gets into kind of geometry, but we basically have the angle similarity. So if you kind of imagine just dropping what's called a perpendicular or an altitude or a height, however you want to say it, dropping that down, that would create a 90-degree angle here. So these are both 90-degree angles. And if you think of this one, this purple angle is the same in the blue triangle and the larger black triangle. So if we're looking at this, we're really looking at this setup right here. So compare this small blue triangle to the larger black triangle. And hopefully it's clear by that there'll be similar triangles. Now, when you're thinking through similar triangles, the best way to think about it, and again, whenever you're dealing with a proportionality for similar triangles, there are multiple ways to do it right and only one way to do it wrong. So the way that I like to do it normally, and again, you could do it slightly differently, but I like to create a little matrix. So like with 4 quadrants, basically. So over here, we'll do big and small. So the big triangle and the small triangle. And then over here, we can think of our 2 measurements. So what are our 2 measurements? I guess the R, and H. So on the big triangle, what is big R? The radius of the big triangle, 26. What is R of the small triangle? R of the small triangle, R of T. That's the function that changes over time. And then what is H on the big triangle? Well, that's 8. And then what is H on the small triangle? So H is small, that's H of T. That's the function that changes over time. And then if you just create an equal sign here and then division, now you have your proportionality. And again, there are other ways you could have done it. What you can't do, you can't do this one big, this one small, and that one small, that one big. You can't swap them. But as long as you're consistent with how you label things, this will always work. And remember, our goal here is to find R as a function of V or H. In this case, it'll just be H because volume doesn't really show up here, looking at it this way. So hopefully it makes sense that if I solve this, and I'm going to pull this down a bit, hopefully it makes sense that if I solve this for R of T, I will get basically 26 over 8, which we can simplify. If we divide by 2 on both sides, that'll be 13 over 4. So 13 over 4 times H of T. And I'm just solving this proportionality algebraically. So basically cross multiply. Cross multiply, divide by 8. So there we go. We came up with an equation for R of T as a function of H of T. Mission accomplished. So now we can just, every time we see R of T in the original equation, we can substitute that. Now things are getting crowded here, so I'm going to pull this down and we're going to actually do that. But hopefully it makes sense that if I make that substitution, what I can do, my new equation becomes V of T equals pi over 3, and then 13 over 4, whatever that is, H of T, the whole thing squared, times H of T. And then if I simplify this algebraically, I can just keep working this down. So this will actually be, and I won't simplify everything. I'm going to kind of leave the constants here, but pi over 3 is one constant. And then we're going to have 13 over 4, the whole thing squared. And I'm just going to leave that, leave that all as one constant for now. And then hopefully it makes sense that I'm going to have H of T cubed. So now this is what we're dealing with. So there we go. So, and actually let me pull all this down again, because I know I'm doing a lot of work here. So at this point, we have we have done what we wanted. So we got rid of the thing. We now have h of t only. We've gotten rid of r of t from this equation successfully. Now we can take the derivative of both sides with respect to time. So if I pull this down, basically what we're going to do here, we're just going to take the derivative, again, with respect to time, not x or y or anything like that, but just with respect to time of both sides. And then on the left side, we're just going to get dv dt, nothing special there. The derivative of volume with respect to time. And then on the right, you can think about this as a constant. We can basically, I'll just pull out this constant again. According to the constant multiple rule, we can just pull the whole thing out. 13 over 4. And again, we'll solve this later for simplification. Oftentimes you will be rewarded if you do not simplify it immediately, because some things oftentimes cancel out. So I'm just pulling this constant out, and then we have h of t cubed, the derivative of that with respect to time. Now here, this is effectively implicit differentiation. I'll just say that. So if you had like d dx of y cubed, how would that go? Hopefully it makes sense. That would be 3y squared dy dx. We're doing something similar, except it's instead of y and x, it's h and t. So basically, when we're doing d dt, again, to understand why implicit differentiation makes sense, you can check out one of our other videos. But for this, we're effectively doing something like this. So h is now, instead of y being a function of x that we're implicitly differentiating, now h is a function of t that we're implicitly differentiating. So it's still going to be basically 3h squared dh dt. And again, that's implicit differentiation that causes that to be true. So this is going to be 3 times, actually I'll write it like this, 3 times h of t, the whole thing squared, times dh dt. So that's good. And now we can simplify things a little bit. So this 3 and that 3 cancel, so that's good. But basically, we're going to have dv dt equals, I'll just say pi times 13 over 4 squared, or sorry, this should be squared. I just noticed, not to the 4th power, squared, times h of t squared times dh dt. So there we go. We've now done step 5. Take the derivative of both sides with respect to time. I guess I should cross this out in the other direction because that's what I've done with the others. So there we go. Now, for step 6, we want to isolate what we want, plug in what you know, and solve. So to do this, I'm actually going to go back up to the top, and I'm going to grab what we originally started with. So I'm just going to pull this down. So this is all the stuff that we know. I'll just pull this over to the side here. So we're trying to solve for dh dt. So for step 6, isolate what you want, plug in what you know, and solve. We're trying to isolate dh dt. So basically, we want to algebraically get that by itself. So hopefully it makes sense. I'll just leave that by itself over here, dh dt, and then equals, and then over here this is gonna get a little crowded, but hopefully it makes sense, dv dt, and then I'm just gonna divide everything on that side by this. So pi times 13 over 4 squared. Again, this is all just a constant. This is just some number, but I'm leaving it this way in the hopes that certain things cancel out. That's what often happens. But basically, just divide everything by this on both sides, and hopefully it makes sense. We've now successfully isolated what we want, dh dt. So we've isolated what we want, plug in what you know, and solve. So here's what we know. So that thing just equals 12, because we know that. Now here, the only other thing we need to plug in is h. But you'll notice we did come up with a way above to find what h of t is at this point in time if we only know what r of t is. And that is using this equation. Remember, we came up with an equation based on similar triangles that tells us that this equation has to relate r of t and h of t at every point in time. So what we can do now is we can basically solve this for h of t. So we can say h of t is equal to 4 over 13 r of t. And then we know that at this point in time that we're talking about here, r of t is 10. So if we plug this in, basically the point in time where they are talking about is going to be where h of t is 4 over 13 times 10. And then I'll just basically move this over there. So that's effectively what we're doing. So now this is using this is a little bit, more roundabout, but we can figure it out based on the equation, based on the similar triangles equation that we came up with earlier. So I know this is getting crowded, so let me copy this down. So I'm going to copy this down, and then we can basically plug in everything that we know. So this is I'll just leave this on the right. This is the equation. And then dv dt is 12, based on what we said before. And then we'll have pi. And then I'm going to move this inside. So it'll be 13 squared over 4 squared. And then times, what is h of t? You could say 40 over 13. I'm going to leave them separated because I can tell basically that a lot of things will cancel out here. So I'm going to leave this as 4 over 13 times 10, the whole thing squared. And that is the HDT. So that's good. Now if you think about this, we have dHdt equals a bunch of numbers basically put together algebraically, so we can simplify this. So if we simplify this, what would we get? We would get 12 divided by pi. And then I'll leave this for now, 13 squared over 4 squared. And then 4 over 13, if we basically square both of these, hopefully it makes sense, we'll get 4 squared over 13 squared, and then times 10 squared. And this, you can see, this is what I was talking about before. Those actually cancel out. So at the end, we get, what do we get? We get 12 over 10 squared. That'll be 100 pi. That is dHdt. And then here we can simplify it down. If we simplify it down, hopefully it makes sense. Divide the top and bottom by 4. So we'll get 3 over 25 pi. So that should be dHdt. So there we go. That's our answer. Now, so this is the answer. So we solved the problem. And now the next question is, like, how do we make sense of this? Or does this answer make sense? So it's always useful, I think, to do these at the end of each problem. So what I'm going to do, I'm going to copy the original question and diagram down, and we'll just see if this makes sense. So this is what we're dealing with. Basically what this says is that if we're pouring in water at a certain rate, when the radius is 10, apparently we got that dHdt equals 3 over 25 pi. And by the way, one other thing we can do here is determine the units. So if the volume is cubic meters per second, and then radius is measured in meters, then hopefully it's clear that meters is actually being used to represent distances. And h of t is measured in meters, therefore dHdt, the derivative, should be measured in meters per second. So hopefully it's clear that the units here are going to be meters per second. Now, what does this actually mean? So if we pour in water, the volume is increasing because the amount of water going into the container is increasing. And if the volume of the cone, of this blue cone, is increasing, so in the water in the shape of a cone, effectively, if that's increasing, doesn't it make sense that the height must be increasing? So the derivative should be positive. Yes, I would say it does. So this number does, again, assuming we did all the math right, this number does make sense, at least in terms of the sign. Now, if the problem was different, like we mentioned previously, and water was leaking out of the bottom at 12 cubic meters per second, then this dVdt would be negative, and then you can see why our answer would be negative. So the math will tell you what the right answer is. It's useful sometimes to double check it to see that to make sure everything makes sense and that you did everything correctly. But overall, hopefully this makes sense. If you have any other questions on related rates or anything else, don't hesitate to reach out to us in the comments. And if you are interested in tutoring, you can basically check out our website. All the info is in the description, but hopefully that makes sense, and have a good day.